73 seconds. That's how long it took 73 seconds from liftoff to a fireball in the sky. On the morning of January 28, 1986, millions of Americans were watching live television. School children gathered in classrooms, teachers rolled in TVs on metal carts. Families paused their day because that morning something historic was happening. For the first time, a civilian schoolteacher was going to space. The shuttle rose into the cold Florida sky. It looked perfect, powerful routine. Then a flash, a burst of smoke. The vehicle split apart, and in less than 2 minutes, 7 lives were gone. This was the Space Shuttle Challenger disaster. But the explosion was not the beginning of the story. It was the end of a chain of warnings that were heard and ignored. In the early 1980s, the United States wanted something bold. Reusable spacecraft, frequent launches. A future where space travel became routine. The program was led by NASA. The Space Shuttle was marketed as safe, reliable, almost airline-like. Launch, land, repeat. Challenger was one of the orbiters in the fleet. By 1986, shuttle launches were no longer rare spectacles. They were becoming normal, and that normality created something dangerous: complacency. The shuttle system was incredibly complex. 2 solid rocket boosters, an external fuel tank, the orbiter itself, millions of parts. Thousands of contractors, one launch schedule that was constantly under pressure. NASA wanted 24 launches per year. That pace demanded confidence. Even when confidence wasn't justified. The flaw was small, a rubber seal. Inside, the solid rocket boosters were segments joined together. Each joint was sealed with rubber O-rings. Their job was simple: prevent hot gases from escaping during ignition. If they failed, superheated gases, over 5,000 degrees Fahrenheit, could burn through the rocket casing. Engineers at a contractor company, Morton Thiokol, had concerns for years. They noticed something troubling. On previous launches, the O-rings had shown erosion, burn marks, damage, especially during cold weather. And January 28, 1986, was cold, colder than any previous shuttle launch. Overnight temperatures dropped below freezing. Ice covered the launch pad. Engineers knew rubber becomes brittle in the cold. They feared the seals would not expand fast enough to contain the explosion at liftoff. They recommended, do not launch below 53 degrees Fahrenheit. That morning, it was 36 degrees. The night before launch, engineers held a teleconference with NASA officials. Charts were presented. Concerns were raised. One engineer said clearly, if we launch tomorrow, we are accepting a catastrophic failure. But NASA was under pressure. Delays had already pushed the schedule. Political pressure was building. Media attention was intense because a teacher, Krista McAuliffe, was on board. NASA managers asked for proof, not suspicion. Proof. The engineers had data, but not perfect data. The damage pattern wasn't clean. The charts weren't visually persuasive. In that meeting, something subtle happened. The burden of proof shifted. Instead of NASA proving it was safe to launch, engineers were asked to prove it was unsafe under pressure. Management at Morton Thiokol reversed the recommendation. They approved the launch, not because the risk disappeared, but because uncertainty remained, and uncertainty was interpreted as acceptable. 11:38 a.m. Challenger ignited. Flames burst from the boosters. The shuttle cleared the tower at 0.678 seconds after liftoff. A small puff of black smoke appeared near the right booster joint. It was the O-ring. Cold rubber had failed to seal instantly. For a moment, aluminum oxide from combustion temporarily plugged the gap. The launch continued. Everything looked normal. NASA's announcer said, "Challenger, go at throttle up." 73 seconds after liftoff, a plume of flame escaped the booster. It struck the external fuel tank. Liquid hydrogen and oxygen ignited. The shuttle disintegrated. The explosion wasn't a typical detonation. It was structural breakup under extreme force. Debris fell into the Atlantic Ocean. Millions watched in silence. Mission control froze. Someone whispered, obviously a major malfunction. The crew: Francis Scobie, Michael Smith, Ronald McNair, Ellison Onizuka, Judith Resnick. Gregory Jarvis, Krista McAuliffe. They weren't just astronauts. They were symbols of progress, of optimism, of national pride. Schools across America had been watching live. Children saw tragedy unfold in real time. The emotional shock was immediate. The shuttle program stopped. The nation mourned. But grief soon turned to questions. How could this happen? Had no one known? The government formed the Rogers Commission to investigate. Among its members was physicist Richard Feynman. During a televised hearing, Feynman performed a simple demonstration. He placed a piece of O-ring material in a glass of ice water. After a few minutes, he removed it. It was stiff. It did not return quickly to shape, he concluded. I believe that has significant bearing on our problem. The investigation revealed engineers had warned NASA repeatedly cold temperature risk was documented launch pressure influenced decision-making. The final report stated clearly the disaster was caused by O-ring failure due to cold weather, but more importantly, it was caused by flawed decision processes, communication, breakdown, normalization of deviance. Over time, minor O-ring erosion had been accepted as normal because it hadn't yet caused catastrophe until it did. This term became central to understanding the disaster. When small failures occur repeatedly without disaster, they begin to feel acceptable. Risk becomes routine. Warnings become background noise. NASA had seen O-ring damage before, and because the shuttle survived, they adjusted their definition of safe. The line moved gradually, almost invisibly, until it crossed into fatal territory. The Challenger disaster wasn't just mechanical failure. It was psychological failure, organizational failure, cultural failure. After Challenger, shuttle flights were suspended for 32 months. Booster joints were redesigned. Safety reporting systems were strengthened. NASA restructured decision authority. But history has a pattern. 17 years later, another shuttle, Columbia, was lost during re-entry. Again, warnings had existed. Again, risk had been normalized. The lesson was difficult. Technology improves, human systems remain vulnerable. The explosion lasted seconds, the consequences lasted decades. Challenger was never supposed to fail. Engineers understood the risk, but institutions are complicated. Deadlines matter, politics matter, reputation matters, and sometimes those pressures weigh more than caution. The shuttle that should never have launched did because the danger wasn't hidden. It was debated, minimized, and finally accepted. 73 seconds. That's all it took. And somewhere, in some organization today, a warning is being discussed, a risk is being calculated. A launch decision is being made. The question is, will they listen?